This will be an introduction to telescopes in the visual part of the spectrum, and so we'll be looking at just a couple of designs. All right, let's go on and look at different types of telescopes. Refracting telescopes. This is the kind that Galileo made back in the early 1600s. And you can buy modern ones. That one on the right, the white one, is a modern refracting telescope. You can spend a whole lot of money for those things. They look nice. Okay, the one on the left is an old picture of the Yates Observatory telescope. This is outside of, or on Williams Lake, which is up in Wisconsin. And it was paid for by a man who made his fortune with the streetcars in Chicago, and then decided he wanted to be remembered for building the largest refracting telescope in the world, and it's the largest one that was ever built. 40-inch diameter telescope. And so that's it. And on the right is the John Deere telescope that you can see up at the Table Mountain Star Party, or it used to be. I'm not sure the guy's still bringing it up there or not. And I think that may be an 8-inch telescope, but I'm not sure. It might only be a 6-inch diameter. Can't remember, but it's fun to look through anyway, although I wouldn't want to haul that thing around. Okay, here's something that'll help you understand a little bit about some of the terms I've been using. This is forming an image by a lens, and you imagine that coming into the lens are parallel light rays from a very distant object. And when we're doing astronomy, we're always looking at distant objects. And so the light rays are coming in parallel. And when they go through a lens of this type, they'll come to a focus. We call the focal length the distance from the center of the lens to where the incoming parallel light rays come to focus. And so that's the focal length of the lens. And then your eyepiece will also have a focal length. Some terminology that I've been using. The objective lens is the one up here at the front of the telescope. The starlight is coming into it. You can see it up there at the top of the telescope. You can think of the objective lens as being closest to the object. And then down there at the bottom of the telescope is the eyepiece lens. It's closest to your eye. It's not your eye, it's the eyepiece, the piece of glass that you happen to stick in there. And I'll show you some eyepiece designs a little bit later. The objective lens forms an image right there. The eyepiece looks at that image that was formed by the objective lens, and the eyepiece lens is like a magnifying glass, and it magnifies that image that was formed by the objective lens. That's how you get a magnified image. It's a combination of both the objective lens doing some work on the object and the eyepiece lens doing some work on it. And the magnification is the focal length of the objective divided by the focal length of the eyepiece. And the eyepiece magnifies the image. It just acts like a magnifying glass. The Galilean refracting telescope, and it starts off with you call this a convex lens in front of it. That's the kind on a typical magnifying glass. And then he used a concave lens for his eyepiece. And this has a slight advantage in that it makes the image you're seeing upright, but it has the disadvantage that it's got a very narrow field of view when you do this. And so you don't see things all that well through it. Kepler's design, on the other hand, used two convex lenses, two magnifying glass type lenses. You can have a wider field of view with the Kepler telescope, and the image will also be brighter. And so you can use a much larger objective lens with this type of telescope. On to the other types of telescopes, Newtonian reflectors. And this is a sketch from your book. This is showing what we call the light path of this kind of a telescope. Now down here at the bottom of the telescope we have the objective mirror, and then in this type of telescope we have a secondary mirror, or sometimes called a diagonal mirror, because it's put at a diagonal to the light from the objective, which is coming to a focus, and it bounces it out the side of the telescope. The objective mirror forms an image right there, and then the eyepiece, which is right there, magnifies the image. And so that's the way that a Newtonian reflector happens to work. And here are a few different types of telescopes. The Newtonian focus, a prime focus, a Cassegrain focus. I don't know how to pronounce that D one right there, but just different designs for different purposes. Newtonian reflecting telescopes are nice for inexpensive amateur telescopes. Here are a bunch of different eyepieces. I don't know why those two popped up all of a sudden, but I meant to go through these in order. The eyepieces are actually combinations of lenses, and you can see how complicated the Earthful and the Nagler 2 down there are. Naglers are made by, well, the Nagler company, I think. Al Nagler is the optician, and he was up at the Table Mountain Star Party one year. His eyepieces are expensive, a few $100s a piece, and most people get several different eyepieces of varying focal lengths, so you can get different magnifications of them. But if you're buying Naglers, you're going to be spending a few $1,000s on eyepieces. You may spend more on your eyepieces than you did on your telescope. I would, because I only paid $500 for my telescope. It's a 10-inch Newtonian reflector, and I don't think I'm going to be buying any $500 eyepieces, or any that'll add up to much more than that either. Some advantages and disadvantages of these different types of telescopes. For refracting telescopes, advantages: you have a closed air tube that can prevent air currents. Believe it or not, air currents can be a problem in a telescope. If the mirror, for instance, is hot and cooling down, you'll have convection currents of air above it, and those can mess up your images. So in a refracting telescope you won't have things like that. There isn't any obstruction in the light path as there is in a reflector. Remember, that diagonal mirror is sitting right in the light path. So you can get better contrast in images because of that. They look cool, like a telescope should look. Disadvantages: they are expensive. Recently I looked up a 10-inch diameter refracting telescope, and I paid $500 for a 10-inch diameter Newtonian reflector, and it's a pretty darn good telescope. But a 10-inch refractor would cost more than $20,000, and I don't think I'm going to spend that kind of money on a telescope. There are people who would, but not me. They also have chromatic aberration, can have that, which is a separation of color that can occur as the light goes through the lens. It acts like a prism a little bit because of an effect called dispersion. It turns out that the focal length is a different distance depending on the color of the light, and so you get separation of color. Now, there are ways to overcome that, but you have to have not just one objective lens, but 2 or possibly 3. And when you're doing that, that's the heaviest part of the telescope. You're having to put those 2 or possibly 3 pieces of glass highest in the air on a reflecting telescope. And they're not worth making large. The biggest telescope, refracting telescope ever made, was 40 inches in diameter. I don't know if it has a doublet lens or a triplet lens on it. It may just have a single lens, so it's going to have chromatic aberration. There's an amateur astronomer, used to live in Spokane, I don't know if he still does, but he made his own 40-inch diameter reflecting telescope. Ground the mirror, built the whole thing. And that's something an amateur can do. It was, took months. It'd be about as much work as restoring an old car or something like that. But he came up with a decent telescope. But it would be out of the range of an amateur astronomer, unless he was really wealthy, to build a 40-inch diameter refracting telescope. And glass absorbs light. There's just kind of no way around that. Those thick pieces of glass you're going to have on your objective lens will absorb some of the light. Let's have a look at reflecting telescopes. Advantages: they're less expensive for larger apertures. They can be made huge. There's no chromatic aberration. Oh, one of the reasons, well, the next part here, the heaviest part is lowest, so it's easier to construct and balance one of these things. That's why they can be made huge. They don't have any chromatic aberration because all the wavelengths of visible light reflect off a mirror in the same direction. Now, if you go up towards stuff like gamma rays, they're going to go right through your mirror, so you don't want to use the same design if you're looking at gamma rays, but that's outside the visible spectrum. Disadvantages: air currents can be a problem, but they can also be remedied pretty easily. The mirror on my 10-inch telescope has a little computer fan stuck on it that I could just hook up to a 12-volt power supply and cool the mirror down quickly, so that would get rid of the convection currents shortly after sunset. So pretty easy. Obstructions in the light paths on these can cause odd effects. And you've all seen pictures that look like this, or this, or this. These are caused by the diagonal mirror supports in the telescope. And they usually happen right at the edge of the visibility. When you're looking at stuff that's really pushing the magnification is when you're going to start seeing these things. And here's the deal. Number 3 on here is the diagonal mirror. It's actually behind that thing, the secondary mirror. And then the things numbered 3 on there are the supports, or the vanes that support the diagonal mirror. Now, these are pretty darn heavy duty supports for that thing, and so they're going to cause diffraction spikes. In an earlier video, I've got some pictures taken at the Oregon Star Party showing diagonal mirror supports that are just thin pieces of wire, and so that's something that can be done with those things. Here's some different configurations of mirror supports and the diffraction patterns that they would cause down below there. So you don't have to worry too much about this, but just be aware the diagonal mirror supports can cause diffraction patterns and make some images look a little weird. And a lot of people think that reflecting telescopes look nerdy, so I think they look utilitarian. I would use that term to describe them. It's a tool, and you don't really worry about it. I think this is a very old picture of the 100-inch telescope on Mount Wilson that Edwin Hubble used when he discovered the expanding universe and some other pretty neat stuff in the 1920s. And this was called the Hooker telescope because the person who paid for it was a guy who made his living in selling pipe and iron work and stuff like that for the city of Los Angeles, which wasn't a very big city at the time, but that's the telescope. Here's a more modern picture of it, and it's blurry because I took this on a tour of the telescope, and they said, we'd like you to witness something. And I'd been looking at the telescope, and I could see this part on here that this brown part here, and it's actually kind of a U-shaped thing, but it points up toward the North Celestial Pole, and it can rotate, and when you rotate that, you're changing the declination of the telescope, And then this blue part is the actual telescope, and it can rotate on an axis that connects over here somewhere, and that changes that changes the declination. Rotating the brown part changes the right ascension. And so that's how you aim it. But they flipped this switch, and we're standing on this platform, and you'd swear that the telescope was rotating in there. And I was so puzzled. I'm thinking, oh, why would you change the polar axis of this? It's aligned and set up and everything. And then they flipped the switch off and they said the telescope was not moving. And what had been moving was the platform that we were all standing on. There was about 60 of us on the tour, and the telescope dome itself. All of that was rotating, and the telescope was just sitting there. And it was so well built that we just barely picked up a little rumble in our feet, and we all thought it was because the telescope was rotating. And it was the most amazing thing I'd ever seen. So there's our little tour of visible telescopes. This took a bit longer than I thought, but interesting anyway. Here is something we have to take into account when we start going outside the visible part of the spectrum, that some of these things don't get through the Earth's atmosphere. There's a visual window and a radio window, but if you want to look at gamma rays, X-rays, or ultraviolet, or most of the infrared, or microwaves, or most of the radio spectrum, you're going to have to do something else. And here's a picture from your textbook that basically shows the same thing, that there's an optical window and then a radio window. This time the thing is kind of turned upside down. If the stripes of color go all the way to the ground, then we're getting it, and they show it in a little bit different way. But it's a good thing that gamma rays and X-rays don't get through the atmosphere, and that most of the ultraviolet doesn't get through it either, because we'd have super high cancer rates if they did. That's it for visible telescopes.